it has a predicted sample, meaning when the null hypothesis is true, people know what these test statistic values should look like. They follow certain distributions like normal distributions or chi-squared distributions or p-distributions. So what happens when you do your one study and you measure the consistency of your data with the null hypothesis by calculating a test statistic, a number, what you do is you look that number up in a table on the back of the statistics book. The table tells you what typical value should be for the test statistic when the null hypothesis is true. It tells you what values for the test statistic support the null hypothesis. What you're trying to figure out is whether your one value from your one study is a typical value you'd expect to see when the null hypothesis is true. So from your test statistic, you calculate something called a p-value. P-value is the probability of getting a test statistic value like the one you just observed in your one study when the null hypothesis is true. Saying how typical is this value from this one study when the null hypothesis is true. So it's describing in a probability statement the chances of getting a result like the one you see in your data when the null hypothesis is true. Small p-values means that this value you observe in this study doesn't happen very often when the null hypothesis is true, meaning the data you just observed is not typical when the null hypothesis is true. On the other hand, large p-values means values that you saw for your test statistic happen all the time when the null hypothesis is true. The data you just observed happens all the time, or most of the time, when the null hypothesis is true. So large p-values means the data supports the null hypothesis. Small p-values means they don't support the null hypothesis. And the way we get the p-value is by calculating this test statistic and comparing it to typical values for that test statistic when the null hypothesis is typical values from tables in the back of statistics book. Let me give you a couple of examples how we do that. First, let's look at the simplest thing epidemiologists do. Have a binary risk factor and a binary outcome. You want to compare patients or subjects who received a lifestyle intervention versus subjects who received it. So in a study, to see if the two groups had the same risk of developing diabetes. What happens when you have a study like that? You display your data in a table like this, a 2x2 table. The two rows might represent the groups that you're comparing. Risk factor positive might be the people who received the lifestyle intervention. Risk factor negative might be the people who received the placebo pill. The outcome is what you're observing. First column of people who developed diabetes, the second column of people who didn't develop diabetes. We have N1 people who were given the lifestyle intervention. A of them developed diabetes and B of them didn't. So A over N1 is the portion or the risk of developing diabetes among those people. You have another group of people, N0, who were given a placebo pill. And C of them developed diabetes and D of them did not. So C divided by N0 is the risk, estimated risk of developing diabetes among people given placebo. But in terms of tests of significance, we're interested in a statement that says the risk factor has no effect on the outcome. Risk ratio is equal to 1. The people given the lifestyle intervention and the people given the placebo pill have the same risk of developing diabetes, meaning A divided by N1, the estimated risk among people given the lifestyle intervention, and C divided by N0, risk of diabetes among people given the placebo, are both estimating a common risk, a null risk that everybody has. Because the null hypothesis says that regardless of the intervention you receive, it has no effect, everyone has the same risk. Well, if that were true, best estimate of that common null risk would be to look at everybody. You had T people in your study. M1 of them developed the outcome. M0 did not. So M1 divided by T is your best guess of the common null risk that people have. Risk that people would have if the null hypothesis is true. So what you want to do is compare the actual data you see in your 2x2 table to the data you would expect to see if everybody had the same common null risk of M1 over T. What you're going to do is you're going to build another table using the same N1 people who were given the lifestyle intervention, the same N0 people who were given the placebo pill. In other words, the same T people. Now, what would happen if everybody had a risk of M1 over T? how many people would you expect to develop diabetes among the N1 people if the null hypothesis were true? Well, the N1 times that common null risk, M1 over P. How many of the N0 people given the placebo would you expect to develop diabetes if the null hypothesis were true? It would be N0 times that common risk. What we have in the body of this table is what we'd expect to see if the null hypothesis is true. And notice each of these expected numbers is nothing more than the row total for a particular cell multiplied by the column total for that same cell divided by the grand total. But conceptually, what they represent are the expected number of cases of diabetes in the first column, or non-cases in the second column, that we'd expect to see if the null hypothesis is true. So the data will support the null hypothesis if the values from this table are very close to the values in the previous table. So how do you measure closeness? What we'll do is we will one by one compare the cell count in the expected in the observed table, say A, to the corresponding expected number, N1 times M1 over P. Get a difference, a deviation between what was observed and what was expected to be observed if the null hypothesis was true. Let me give you an example. This is where we're going to calculate, we're going to take the observed numbers, subtract the expected numbers. We're going to all four cells. Oops. I'm going to call that number x squared. And the reason we do this calculation is because if the null hypothesis is true, this number x squared should look like a typical value from a certain theoretical distribution, a chi-squared distribution with 1 degree of freedom. If the null hypothesis were not true, the observed numbers and the expected numbers would be different by an expected larger amount. X squared would be larger. Therefore, larger values for x squared do not support the null hypothesis. They give you some suggestion of the alternative hypothesis. But the actual p-value is calculated by comparing the observed x squared we had to a table in the back of the book, a chi-squared table with 1 degree of freedom, to see if x squared is a typical value we would expect to see if the null hypothesis is true. Another way of saying that is whether the observed table is a typical table we'd expect to observe if the null hypothesis is true, by comparing it to a table we'd expect to observe if the null hypothesis is true. So let me show you how this works in a number. I'm going to use this survey that 21 of you responded to last week when Aaron sent around the survey. We asked you a bunch of questions. One of the questions was, how often do you eat spam each month? And I collapsed that into two categories. I created a variable called eat spam. If you ate spam at least once a month, and you had a value of 1 for that variable. Otherwise, you were coded as a 2. We had another variable saying whether you needed a vacation immediately or within a period of time, like a week or something like that, or within the month. Anybody who said they need it now, I said, you are somewhat stressed out. Let's say you are 1 on that variable. I'm going to compare a risk factor, eating spam, to an outcome, needing a vacation now. Spam as maybe a measure of your dietary intake and whether you eat some type of a diet or another diet, and needing a vacation as an indication of how stressed out you might be. But what did you show, or the 21 of you who completed this survey? This is a SAS printout, and unfortunately, when you write out SAS into PowerPoint, it loses some of its formatting. That's what these little F's mean here. Whenever you see these F's, just think of them as a straight line. What we have in this data set in the row is whether you ate spam, those are the ones, or didn't eat spam at least once a month. 11 of you said you eat spam at least once a month. 10 of you said you don't. So half of you guys are eating spam at least once a month, which is a lot more than I eat it. I don't know when I ate spam last. Actually, it wasn't when I was in Hawaii last year, that's for sure. It was probably when I was in college or something. But of the 11 of you who ate spam, 5 of you profess that you need a vacation right now. That's 45% of you. Of the 10 people who don't eat spam, 6 of you said you need a vacation right now. That's 60%. So notice the risk of needing a vacation right now is actually lower in the spam group, 45% versus 60%. If you calculate a risk ratio, 45 over 60, you get a risk ratio of about 0.75 from this data set as a measure of association between spam consumption and needing a vacation right now. But the question is this a statistically significant result? Is your risk ratio 45 divided